Hi everyone, my name is Jeremy Peacock and I'm coming to you virtually today to talk about how we can leverage the cross-cutting concepts to support three-dimensional learning in middle and high school science classrooms. You see my email address on the screen there, and I would encourage you to reach out to me with any questions or any way that I can help you following this session. We'll start today with a lighthearted graph comparing per capita mozzarella cheese consumption to the number of civil engineering doctorates awarded. Along with the graph, we see a sample headline that we might find on a website trying to get us to click onto this news article. Are civil engineers eating too much cheese? Experts weigh in. Why does this matter, and why does scientific thinking matter? Before we dive into those questions, let me point your attention to that icon up at the top right and to the instructions down at the bottom of the slide. Anytime you see that icon, you'll know that it's time to pause and do some reflecting. And I've created a reflection guide to support you throughout the session. If you take that bit.ly address and type it directly into the address bar of a new browser tab, it will take you to a copy of the Google document that I created. You can use that Google document to collect your thoughts as we work through, and there are also some activities embedded that you'll complete within the document. I'll jump over there and give you a little bit of a tour, and then we'll come back to continue the presentation. So here we are in the reflection guide. You should have your own copy of this now, and you can edit that copy any way you see fit. Be sure to save that to your drive so you'll be able to find it easily later. If you're working alone, this will be pretty straightforward. The document just gives you a place to answer reflection prompts as we work through the session. There are also a few times where you'll do some interactive activities like this card sort where you can drag these images over to match up. I'll explain those as we go along. If you have the luxury of working with a group of colleagues, then you can do the full version of those activities, which really are designed to be done in a face-to-face setting with a lot of interaction and discussion. Those activities mainly were designed by the California Academy of Sciences for a professional learning module that they developed focused on the cross-cutting concepts. And you can find all the instructions and resources for the full activities by following this bit.ly link here. Let's get back over to the presentation and move along. Okay, now that we're back to the presentation, let's talk more about this graph. This will be your first chance to actually use your reflection guide, and I want you to answer this question. How did this graph and headline illustrate the importance of scientific thinking in our society? Pause the video, take a moment to record your thoughts in the reflection guide, and then hit play when you're ready. Okay, now that we have our reflection guide set up, we'll continue with the presentation. Also notice that icon in the top right of the slide. Anytime you see that, then you'll know it'll be time to go over to the reflection guide and do some thinking or complete one of those interactive activities. Here's our first question. How do this graph and headline illustrate the importance of scientific thinking in our society? Pause the video, take a moment to answer that, and then hit play when you're ready. Whenever I ask teachers what they really hope students take away from their science classes, they rarely talk about content knowledge. We do want kids to learn some things about science, but what's much more important to most teachers is that students learn how to solve problems. They learn to be critical thinkers. They learn to apply what they learn in the classroom to the world outside of school. Every news cycle today reminds us of the importance of helping our students become critical consumers of science-related information and helping them to be able to use that information to make decisions for themselves and their family and our society. Framework for K-12 Science Education is a document that compiled research about how students best learn science and made recommendations about the kind of science learning that should be embodied within science standards. This document was the foundation for the revision moving from the Georgia Performance Standards to the Georgia Standards of Excellence. The framework lays out a goal where students, by the time they graduate from high school, can use the three dimensions, those practices, cross-cutting concepts, and core ideas, to engage in public discussions on science-related issues, to be critical consumers of scientific information in their everyday lives, and to continue to learn about science throughout their lives. The other thing that the framework makes clear is that these goals apply to all students, not just a subset who might go on to become scientists or engineers. Let's take a closer look at those three dimensions just to make sure we're all on the same page. On the left there, you see the science and engineering practices. Those are the statements that start out every single standard and element throughout the GSE. Things like asking questions, developing models, engaging in argument from evidence. At the top right, you see the disciplinary core ideas. That's the content. And at the bottom right, you see the cross-cutting concepts, and we'll be focusing on those a lot throughout this session. In the middle, you see phenomena and solving problems. So the goal of three-dimensional learning is always to have students engaged in making sense of phenomena or developing solutions to engineering problems. Here's your second chance to jump over to the reflection guide and put down some of your own thoughts. Why are the cross-cutting concepts important in three-dimensional learning? What's their purpose? Take a moment to answer that question, and then continue the video when you're ready. To put the cross-cutting concepts in context, it's helpful to think about what each dimension really represents. The science and engineering practices are what scientists and engineers do in their professional lives, and we want students to be engaged in those same activities. The core ideas represent what scientists and engineers know and the type of knowledge that they need to solve problems and develop explanations. And the cross-cutting concepts represent the ways that scientists and engineers look at and think about the world around them. And we want to help kids develop those same patterns of thinking across their K-12 career. Okay, going back to your reflection guide in a moment here, but this time you're going to do more than just answer a question. We're going to complete the speed dating activity. That name comes from the face-to-face version of the activity. And if you have the luxury of working with your colleagues, you can go to that bit.ly address at the bottom right and download the full instructions and materials. If you're working alone in the reflection guide, you'll see a table that looks like the one on my screen. What you'll do is drag the images from the card bank column into the correct cell on the definition column to match them up with the correct cross-cutting concept. This will be a simple activity for most of you, but it will just make sure that we all have a basic familiarity with what each cross-cutting concept means. Pause the video, take a few minutes to work through that, and then hit play when you're ready. Okay, so how did you do on that? Here are the descriptions of each of the cross-cutting concepts matched up with the correct concept. Were any of these definitions surprising to you? If so, why? Take a moment to answer that in your reflection guide, and then continue the video when you're ready. So now that we have some basic background about the cross-cutting concepts, we need to ask ourselves a question that researchers have asked over and over. If we think about 3D learning, are the cross-cutting concepts a critical component, or are they the proverbial third wheel like the little girl on the right? Let's go back to the framework and see why the authors of that document felt it was important to include the cross-cutting concepts in the three-dimensional model. You can see from these first few sentences of the chapter introducing the cross-cutting concepts that their major role is bridging the different disciplines of science, connecting biology to chemistry to physics, etc. The cross-cutting concepts also perform two other major roles: providing students with an organizational framework for connecting their knowledge, and helping students build a coherent and scientifically based view of the world. For most of today's session, we're really going to dig into those last two goals and break them down even further. We'll start by looking at the cross-cutting concepts as an organizational framework and thinking about how this can support student learning. This slide will serve as an outline as we work through the different roles that cross-cutting concepts can serve. As I mentioned, we'll start by looking at the cross-cutting concepts as a framework, and then we'll get on to those four other roles and talk about them a little bit separately. What I want you to do now is think about an area in which you consider yourself to be an expert. Teaching might be the obvious choice, but maybe you have a specialty within education like gifted or special education. Maybe you have a specialized graduate degree. Maybe you're a coach or a former athlete, or maybe you have a hobby or had a prior career before education. Whatever the case may be, I want you to think about how your knowledge in that field is different from someone who's new to the field. So what we're trying to think about here is how experts differ from novices. Take a moment to answer that question in your reflection guide, and then continue the video when you're ready. To start this discussion, let's look at a study that involved novice and expert chess players who were asked to memorize the position of individual pieces on a board in mid-game positions. The novices and experts took very different approaches to this task and came out with very different results. Novices focused on individual pieces and memorizing the position of those individual pieces on the board. The experts took a much different approach. they focused on patterns that were based on chess strategy. So they focused on whether pieces were in attacking positions or defending positions or still in their initial positions. Using this system to organize their knowledge, the expert players were able to memorize the positions more accurately and more quickly than the novices. When we talk about using the cross-cutting concepts as organizational frameworks, what we're really saying is that we want to help students move from thinking like novices to thinking more like experts. If we take an example from chemistry, we might think about a beginning student who's trying to memorize isolated facts about chemical elements. Here they have a list with names and symbols and atomic numbers, and the list is in alphabetical order by name because the beginner might feel like that's a good way to organize the information. A chemistry expert knows that a much more meaningful way to organize this information is using the periodic table, and that expert would focus more on the patterns that emerge within the periodic table rather than memorizing isolated facts. This report from the National Research Council was one of the documents that served as the foundation for the framework for K-12 science education, and it offers some more background about expertise. Experts, as we just saw, notice features and meaningful patterns of information that novices just don't see. They have a great deal of knowledge that's organized in ways that reflect a deep understanding of their field. We saw that with the chess players as well. They have knowledge that is contextualized based on its application. What that means is they don't remember information just for the sake of memorizing trivia. They remember information in the context of how it helps them solve problems or develop explanations or answer questions in their field. They remember information based on its application. Experts can access their network of information with very little effort. One interesting side note is that experts are not necessarily able to teach others. It makes me think of the sports analogy that the greatest players in a sport generally don't make great coaches. But that's an aside for us. Finally, experts have varying levels of flexibility in approaching new situations, and there are sometimes even benefits to having a non-expert look at a problem or a question because they may bring a more creative approach to solving it or answering that question. But in general, there's a lot of value in expertise, and the more that we can help our students move toward thinking like experts, then the more we can help them move toward those goals that we laid out at the beginning of the presentation. Going back to the framework, we now want to shift our focus to the final part of this statement. The goal here is to help students develop this coherent and scientifically based view of the world. How do you think the cross-cutting concepts can help us achieve that goal? Take a moment to answer that question in your reflection guide, and then continue the video when you're ready. Before we really dive into that question, we need to remind ourselves about the overall goal and how the cross-cutting concepts fit into that. Our goal in three-dimensional science learning is always to have the students engaging in all three dimensions to make sense of phenomena. We never want to use the cross-cutting concepts in isolation. The same is true for the practices and the core ideas. We always want students using all three dimensions to make sense of a phenomenon. So we really should never be talking about the cross-cutting concepts without talking about a phenomena and those other dimensions. So we need a phenomenon of our own to focus on throughout this session. This phenomenon comes from the Carbon Time curriculum, which was developed out of Michigan State University. You can view this video on its own by following that first bit.ly address, and then if you want to see the video in the context of that full curriculum, you can follow the second bit.ly address. I'm going to go ahead and play through this, though, within our presentation for our reference.
And today, we're feeding mealworms.
Okay, Nina. This investigation is about mealworms. We'll have a worm's eye view of these guys chowing down.
We're going to have some happy mealworms because they're going to get served dinner. Yummy!
When an animal like a mealworm eats something, we can see on the macro scale that it chews the food up and swallows it. But what exactly is happening that's too small for our eyes to see? How are mealworms changing matter and energy when they eat, grow, and move?
What's happening at the molecular level with atoms and molecules?
We want to understand what's happening chemically when mealworms eat and grow. To do that, we ask three questions.
The movement question.
Where are atoms moving?
The carbon question.
What is happening to the carbon atoms?
And the energy question.
What changes in energy are taking place?
We can learn more by weighing mealworms and their food before and after they feast. BTB is bromothymol blue. BTB changes its color when carbon dioxide is added, like when you blow bubbles into it. We can use BTB to see if carbon dioxide concentrations increase in the air when the mealworms are eating. So let's make some predictions. What gains mass? What loses mass?
And don't forget carbon. What is happening to the materials with carbon atoms?
Is energy involved here? Where would it be coming from? How would it be changing? What do you think will happen? Be sure to explain your predictions as we pause the video. Okay, let's start our investigation and see if your predictions were right.
Before mealtime for the mealworms, make sure you've got your scale, your potato, your BTB, and the stars of this investigation.
The mealworms. We start by weighing our worms.
We have the weight of the worms on our shoulders.
What?
Like, weight of the world? Never mind. We'll want to weigh all the worms and also the potato to fully understand the mass change. Well-balanced mealworms.
Here's a sample chart from another classroom with starting mass data. Our potato started out at 12.5 grams, and the mealworm started at 15.4 grams. And we're putting in our dish of BTB to detect any changes in the concentration of CO2. Our starting color is blue, and we'll need to mark that on our data chart.
These little guys will grow up to be beetles someday. They need to chow down and put on some pounds.
Maybe not quite pounds, but we'll see. Now, it takes about a day to feed the mealworms, so we'll speed this up.
Wow, they're hungry.
Eat up, everybody.
Okay, time to weigh everything now that the feasting has ended. And here are our mass changes. We started with 15.4 grams of mealworms, and now we're up to 15.9 grams. That's a gain of 0.5 grams. And the potato went down from 12.5 to 11.3 grams. That's a loss of 1.2 grams. And our data are right in line with the data from another classroom. These are our data, but you have data too. How do your results compare with those on the chart? Is there a pattern? Pause the video and discuss. So, looking at the data, it looks like all the mealworms gained mass, but not as much mass as the potatoes lost.
If the mealworms gained mass, that means that atoms moved into them. But something else is going on too. The mealworms didn't gain as much mass as the potatoes lost.
So where did that extra mass go? Could the mealworms be losing mass at the same time as they're gaining it?
The BTB should provide a clue. We had a color change.
The BTB turned yellow, indicating that carbon dioxide is going into the air.
Where did the carbon dioxide come from? One more thing. It looks like the mealworms are moving around a lot. Where did they get all this energy?
Lots of things to review. And some unanswered questions. There were definitely atoms moving. The potato lost mass. The mealworms gained mass, but not all the mass. Where did the missing mass go?
The CO2 concentration increased. So where did carbon atoms in the carbon dioxide come from? And finally, the mealworms are getting energy to move around from somewhere. How are the mealworms getting energy? What are the mealworms doing with that potato after they eat it?
And look at those full bellies. They're lucky they wormed their way into this one.
Good luck in your investigations.
Okay, so that video gives us a great example of how we can use cross-cutting concepts, in particular energy and matter, to structure student thinking. But you also see that it's not the cross-cutting concept in isolation. Students are conducting an investigation, they're analyzing data, and they're clearly building up to some core ideas related to cellular respiration and metabolism. We'll come back to that phenomenon as we discuss the roles that cross-cutting concepts can play beyond serving as an organizational framework for students. Here's that slide that I said would kind of serve as our outline as we go through the bulk of the presentation here. We talked about cross-cutting concepts as an organizational framework. The other four roles that we're going to look at come from an analysis by Ann Rivett from Columbia Teachers College and her colleagues. And what they did was to look at the framework for K-12 science education, the next generation science standards, and some other supporting documents, and they analyzed how the authors of those documents described the cross-cutting concepts, how they meant for them to be used, and they came up with 4 roles. That is that the cross-cutting concepts can serve as rules, which we'll talk about that one first. They can serve as lenses, they can serve as bridges, or they can serve as tools. And we'll walk through each of those roles, provide some examples, do some reflection, and provide some resources that will support you in integrating the cross-cutting concepts in your own classroom. Let's start by focusing on the rules. And that video of the mealworms is a great one to kick off that discussion because the heart of that video really is conservation of matter. When we think about the cross-cutting concepts as rules of the scientific game, we can think about benefits of that approach and some limitations. Thinking about cross-cutting concepts as rules helps us define what science is. That is the epistemology of science. Rules also provide us with a shared language and shared representations in science. And they allow students to get into the game. They help students start moving down that road towards expertise because they understand the ways that scientists think and talk and communicate and answer questions. Some limitations are that knowing the rules doesn't make you a player. I know some football rules, but I'm no football player. But it's also true that I can't get into the game if I don't know those rules. So knowing the rules is necessary, but not sufficient. It also can be a challenge to connect students' understanding of what it means to do science with practicing scientists' understanding of that. And that's especially true when students have prior school experiences that don't reflect the true nature of science. But think back to the video, and particularly the role that the rule of conservation of matter played in structuring student thinking in that video. Now, in your reflection guide, think about a rule in your own discipline, and if you're a chemistry teacher, try to think of something other than conservation of matter. How could you use that rule to support student thinking beyond rote application? And I put that last note there because I think of a professor at UGA that I talked to years ago who described chemistry students in his freshman class who could balance equations all day long, he said, but they couldn't tell you what was inside the bubbles of boiling water. So we need students to use rules in ways that support conceptual understanding, not in ways that are just mechanical. Pause the video, answer that question in your reflection guide, and then come back when you're ready. Let's take a closer look at conservation of matter and how it develops in our Georgia science standards over time. Second graders learn that small pieces can be rearranged to make new objects. Fifth graders learn that the phase changes in water can be explained by particles that make up the substance. Eighth graders start learning really about chemical reactions, and they focus on the idea that the number of atoms is conserved in a chemical reaction. In physical science at the high school level, we bring in the idea that mass is conserved during physical reactions. And by the time students reach chemistry, they should have mastered this concept of law of conservation of matter, and they should be able to use that concept now to analyze chemical systems through stoichiometry and to understand how chemical systems can be manipulated. I'm going into some detail about conservation of matter here because I want to illustrate how complex ideas can build over time. And that's exactly what happens with the cross-cutting concepts. We're going to go to the reflection guide in a moment here, and this time you're going to complete the second interactive activity. Again, if you're working with a group, then you can follow the full activity by going to the California Academy of Sciences link at the bottom right. If you're working as an individual in the reflection guide, you'll see 7 tables that look like the one here, one for each of the cross-cutting concepts. On each one of them, you'll want to drag images from that third column to match up to the correct grade band in the middle column. So you're trying to determine which one of those images on the right describes the cross-cutting concept at the K2 level, which one describes it at the 3-5 level, and so on. There are further instructions in the reflection guide, so follow those to complete the activity. You'll also notice that below each table is a link to check your work by visiting the NSTA site. They provide some really nice matrices that lay out the descriptions of the cross-cutting concepts across these grade bands. Go over to the reflection guide, complete this activity, and then come back to the video when you're ready to continue. Okay, so here we are in the reflection guide, ready to complete the vertical alignment card sort activity. You see number 7 here, and this just gives you brief instructions and has the reflection question, but the actual activity is down lower in the document. So you'll want to follow this link here. It says vertical alignment card sort, and that's going to jump down to the bottom of the document to a bookmark. And then you can see the patterns table is right here in front of you, and then you could also jump to any of the other 7 cross-cutting concepts by following these links right at the top here. Within each one, you're just going to drag the image over to the correct grade band, like so. That's not the right one. We'll just undo there. And so again, you can complete one or more of these cross-cutting concepts. It'd be great to work through all 7 of them if you have time right now. At the bottom of each one, you can click this link that says check your work. That's going to take you to that NSTA site that I mentioned, where you can actually see the grade band matrices. You can jump back to the top of the card sort, and then when you're finished with this, then we'll click this link that says continue reflection guide, and that will take you back up to where you were back at number 7, and then you can complete the reflection question and then come back on over to the video when you're ready to continue. So as you worked through that, what clues helped you figure out the progression? Go back to your reflection guide and take a moment to answer that. What you might have noticed as you read through those descriptions was that the vocabulary becomes more complex. Often the statements become longer. You may also notice that the earlier grade bands focus on concrete examples, whereas the higher grade bands focus on more abstract concepts. All those things help you understand how the cross-cutting concepts build over time and how we need to support students from kindergarten all the way through 12th grade to help them fully develop an understanding and be able to apply the cross-cutting concepts in the way that we really want. Now we'll look at the cross-cutting concepts as lenses. The benefits of thinking about cross-cutting concepts as lenses are, first, that they allow students to see the unseen and to see phenomena from different perspectives. We can start cluing kids in to some of those patterns and features that experts might notice, but novices might not. They can also help students identify productive questions and sense-making goals. You could see in the mealworm video how the cross-cutting concept of energy and matter generated a series of questions that guided students through making sense of that investigation. One of the limitations of thinking about cross-cutting concepts as lenses is the idea that a certain lens has a certain purpose. If we were to only focus on just 2 or 3 of the cross-cutting concepts, then we would get locked into only certain perspectives, and we might miss some other productive features of phenomena or questions that would help us understand the phenomena. So we want to be careful about selecting cross-cutting concepts appropriately and be flexible about switching between cross-cutting concepts when that's appropriate. It can also be difficult for students to see how one lens can transfer from one phenomenon to another. And so as teachers, we need to help them see those connections. And we'll talk more about connections coming up shortly. Okay, going back to our mealworm phenomenon, we saw the focus on the energy and matter cross-cutting concept, but let's think about how using other cross-cutting concepts might support student learning with this phenomenon. What other cross-cutting concepts could you use to help students make sense of this phenomenon? And then as you think about those, how would this change the student learning outcomes, and how could this benefit students? And again, if you're working in person with your colleagues, you can follow the instructions for the full lenses activity by following that bit.ly address for the Cal Academy of Sciences. Jump over to your reflection guide, answer these questions, and then come back when you're ready to continue. So one of the limitations we just said in thinking of the cross-cutting concepts as lenses is helping students see connections, say, between different phenomena. That brings us to the next role of the cross-cutting concepts, which is the idea that they can serve as bridges. The cross-cutting concepts can support students in engaging in analogical reasoning, that is, thinking about how 2 different things are similar to and different from each other. The cross-cutting concepts can help us make these connections in a lot of different ways. We can look at how different disciplines are connected, so that would be biology to chemistry to physics, etc. We can look at how different phenomena are connected. That might be within one course, moving from that mealworm phenomenon to a photosynthesis-related phenomenon, for example. It might be connecting phenomena from 6th grade earth science to 8th grade physical science. Density would be a concept where we could really benefit from those connections. It might help us connect different levels of organization. That's one that really rings true to me as a biology person when I think about analogies between, say, cell structure and function and then organism structure and function. It can also help us connect science and engineering as two separate fields. And we'll come back to this a little more later in the presentation, it can help us connect, and this is in some way one of its major roles, that the cross-cutting concepts help us connect the core ideas to the practices to fill out that three-dimensional model. As with any of these metaphors for how we can use the cross-cutting concepts, there are some limitations. The challenge here is focusing on productive connections and seeing the connections that experts would see. Students may miss things that would be productive connections. They may see certain things that they think are productive and may turn out not to be. And that's just part of the process of trial and error and learning. We just need to help students move down that road toward understanding those connections in more effective ways and thinking more like those experts. Students are likely to overemphasize similarities as opposed to differences. Both those things are really important, and so we may need to prompt students to think about the differences because they'll tend naturally to focus on how things are similar. All right, we want to look more in depth at this role of cross-cutting concepts, and in this case we're going to focus on how the cross-cutting concepts connect different phenomena. We're going to complete this station rotation activity. Like many of these activities, the name of it comes from, it's designed for in-person professional learning. And if you're with your group of colleagues, then again, you can follow that link to the Cal Academy and download the resources and instructions there. If you're completing it individually in the reflection guide, then you'll see a table that looks like this. What we'll do for the stations is I'm going to walk through a series of 7 slides, and those slides will have 3 or 4 images on them that represent phenomena. And your task is, 1, to think about what is the cross-cutting concept that unifies those 3 or 4 phenomena. And then once you've identified that, think about some examples from your own discipline that also connect well to that cross-cutting concept. And you can use the table in the reflection guide to record that information as we go along. Okay, so here we go. Station 1 provides a little story about 2 friends. I'll let you read that on your own momentarily. We've got a predator-prey graph over time, and then we have a diagram of a Rube Goldberg machine. Pause the video here if you want to take a moment to read that story and to think about how these 3 images are connected. Okay, let's move on to station 2. We see trophic levels in an ecosystem. We see some logs and then a campfire. And then we see that famous equation E equals mc squared. Again, pause if you need to think about which cross-cutting concept connects these examples, and then think of some examples from your own discipline that connect to that same cross-cutting concept. Station 3, we see the moon phases. We see monthly average temperatures in San Francisco and also Perth, Australia. And then we see some information about Fibonacci series from math. Station 4, we see a poster comparing the solar system to a football field. We also see this statement that statistically conclusions based on large sample size are more reliable than conclusions based on small sample size. And we see a statistic here that in the typical education workshop, there are about 4 female participants for every 1 male participant. Station 5, we see a diagram of the rock cycle, and then we see the life cycle for 2 different types of insects. And that graph at the bottom is showing carbon dioxide concentrations in Earth's atmosphere over about the last 400,000 years. Station 6, we see the skull of an herbivore and a carnivore. We see some information about the sustainable design of the building at the California Academy of Sciences. Again, this is one of the activities that they've developed, hence the reference to their building there. And then we see the design of 3 different bridges. And our final station, we see a diagram describing the United States government. We see another diagram of a human body, and then we see a diagram of the water cycle. So for each of those stations, you should have identified what's the cross-cutting concept that connect those 3 or 4 examples, and then also thought about some examples from your own discipline that connect to each of those cross-cutting concepts. If you want to take a moment to check yourself, you can pause on this table, and this just lays out for you which station connected to each of the 7 cross-cutting concepts. Okay, let's go back to our mealworms, and we're thinking about this idea of using the cross-cutting concepts as bridges. So how could we use cross-cutting concepts to help students connect this mealworm phenomenon to other phenomena they have or will experience? So depending on what you teach, this will be a little bit different. But if we think about this phenomenon as happening in a high school biology classroom, then how could you help students either prepare for, connect to, if we're within that biology class, or build on this phenomenon? So if I'm a physical science, 8th grade physical science teacher, then I'll think about how I can use cross-cutting concepts to help students build up to this phenomenon. If I'm a chemistry teacher, then I might think about how I could refer back to this phenomenon as we engage with a phenomenon in the chemistry classroom, and so on. So jump over to the reflection guide, take a moment to answer that, and then come back when you're ready to continue. Okay, so the final role we'll look at is using the cross-cutting concepts as tools. And this is the section where we are most directly going to bring in some resources that are going to directly help you support your students in your classroom. When we're thinking about cross-cutting concepts as tools, the benefits are that we can use the cross-cutting concepts to structure student thinking. You saw in the video the way that they used questions to structure student thinking, and question prompts are one form of thinking of the cross-cutting concepts as a tool. Using them as tools also makes the application of the cross-cutting concept really explicit. If you're using a particular question prompt or a graphic organizer, it will be very clear to the student that they are engaging in the cross-cutting concept of patterns or structure and function or systems and systems thinking. It helps the students identify essential evidence. It helps them figure out what matters at that moment to analyze that phenomenon. And it can leverage their existing understanding of the practices of other phenomena, and it can help them connect to these new phenomena. It can help them transfer their learning from previous experiences to the phenomena that they're currently trying to make sense of. As always, there are some limitations. It does rely on prior knowledge, and so as always, we need to think about how we can help students build and or access that prior knowledge as they're making sense of new phenomena. It also requires some reflection by the student and the teacher on how the tools can be transferred from one phenomena or one context to another. When we get into the graphic organizers, one of the things I would say is that often it's going to be best practice if you modify that graphic organizer to be more specific to that context. Students can then recognize that, hey, this is pretty much the same thing we used last time, but it's also a little bit different. So they can understand how we're transferring the same skills, but you can also scaffold to make it a little bit easier for them to apply the tool in that particular context. So I mentioned that there are 2 big categories of tools here. The first are question prompts. Everything I talk about right here is linked in the resources that are in your reflection guide. We'll talk about those a little bit more in depth later on. One of the great tools in here, though, this comes from the STEM Teaching Tools website, and this is their prompts for integrating cross-cutting concepts into assessment and instruction. But these are really great for in the moment, on the fly instruction. Like these give you questions that you can use directly with your students to engage them in using the cross-cutting concepts to make sense of phenomena. The mealworm video did a good job of illustrating what some of these look and sound like. And what you find in this document is a section for each of the 7 cross-cutting concepts with a page or so or more of different ways that you can frame questions to focus on different aspects of that cross-cutting concept. The second main category of tools here are graphic organizers. That top image represents a set of graphic organizers that I helped develop. We're going to focus on those here in a moment. The bit.ly address will take you to a Google Slides file that has actually 8 graphic organizers. There's one for each cross-cutting concept, but then there's a second one for scale, proportion, and quantity. You can copy that Google Slides presentation, and then you can edit those and use them in your classroom as you desire. The image at the bottom represents a set of cross-cutting concepts that Paul Anderson, you may know him from Bozeman Science. He has a newer website called The Wonder of Science, and he's got graphic organizers and a lot of other tools to support all 3 dimensions. And so the bottom one is one that he developed. Okay. We're going to do some practice here, going back to that mealworm phenomenon. If you need to rewatch that video, you can use that bit.ly address to access the YouTube video. And what I want you to do is use the matter and energy tool. That's one of these graphic organizers that I helped develop. I want you to use that graphic organizer to analyze this mealworm phenomenon. If you look in your reflection guide, you'll see that the graphic organizer is embedded right into the document. It's in there as an image, and so what you'll want to do is double click on that image, and that will take you into the drawing, and then you can edit the drawing to record information. Okay, now that you've had a chance to use one of these graphic organizers, I want you to think about how it helped you make sense of that phenomenon. And secondly, how can you support your students in using it? I imagine they've never really used anything quite like this, and so what are some strategies you could use to introduce them to it and to support them so that they can use it effectively as they're analyzing their own phenomena? Take a moment to answer those questions in the reflection guide, and then come back when you're ready to continue. So that brings us to the end of thinking about these different roles that cross-cutting concepts can play. What you probably noticed as we work through those different roles is that they're not isolated. They really overlap with each other. If you think about using a matter and energy tool, it was serving as a tool. It was also based on the rule of conservation of matter and energy. It was also serving as a lens to focus you on particular aspects of that phenomenon. And if we use that same tool with different phenomena over time, then it can serve as a bridge. And it's certainly helping students to organize their knowledge. What's also true here is that these 5 roles together really accomplish more than any one role can on its own. Ann Rivet, who conducted the analysis that identified those 4 roles on the outside of the slide, in the paper where they presented that analysis, the authors said, no single representation is as useful in isolation as they are together. So it's not a matter of thinking about which one of these roles is the best or the one we should use. We need to be able to move flexibly between them as students and as teachers. Now, this is going to sound familiar. We started off here, I gave a reminder in the middle, and we're coming back to the same idea because it's so important. 3-dimensional learning means that students are using all 3 dimensions to make sense of phenomena. We're focused on cross-cutting concepts today, but we don't want to teach those in isolation. The core ideas are very important. The knowing. Students need to know things about science. Students need to be able to do science. They need to engage in those practices. But the cross-cutting concepts, the specific role they play is tying those things together, connecting the knowing to the doing. So cross-cutting concepts get us to the thinking. And we need students doing all 3 of these things to make sense of phenomena or to develop solutions to problems. We don't want to focus on any one dimension in isolation. Now that you've had a lot of time to dive into the cross-cutting concepts, look at the vertical alignment, vertical progression across K through 12, engage in some different activities around them, you may have started to see some relationships among the cross-cutting concepts. I want you to take a minute and think about that. Go over to your reflection guide and you just have some empty space there. And I want you to use that space to describe any relationships that you see. So you might organize that as a list or a chart or a conceptual model. Any way that makes sense to you will be terrific. But take a few minutes, think about relationships that you see among the cross-cutting concepts, and then come back to the video when you're ready to continue. Okay, so you thought about some connections that made sense to you. Different researchers and authors have come up with some different ways to organize the cross-cutting concepts, but I'm going to share one particular model of connections between the cross-cutting concepts with you right now. This model starts with patterns because that's one of the fundamental goals of science, is to describe the patterns that we see in the natural world. And so that's a common starting place when we think about organizing cross-cutting concepts. The second fundamental goal of science is to explain those patterns, to explain how and why they happen. And so that takes us to the cross-cutting concept of cause and effect. When we think about patterns, thinking about scale, proportion, and quantity can help us identify and understand and describe patterns. It's also true that we can think about how patterns stay the same or change over time. So that brings in the concept of stability and change. And when we start developing explanations for these patterns, two of the big resources we have to explain these cause-effect relationships are what's happening to matter and energy. Again, you saw that in the mealworm video. What's happening to the atoms? What's happening to the energy? That will help us explain why the mass changed the way it did in that investigation. And the second resource that we often rely on to explain cause and effect relationships is structure and function. So I think back to the two skulls that you saw on the station rotation, the herbivore and the carnivore, and how those structures in those skulls reflect the functions that are required for those organisms to survive. Finally, all of this thinking, all of this kind of intellectual effort in science is applied toward thinking about systems. Kind of this idea that an ecologist doesn't see trees or forests, they see an ecosystem and they see parts that are interacting and interdependent. And so systems and system models really provides the context for all the other cross-cutting concepts. So it's kind of the overarching cross-cutting concept here. Again, this is one way to organize the cross-cutting concepts. It's not the only way. This is the way that this author and colleagues presented. There was a lot of the information that I'm sharing today comes from this summit for examining the potential of cross-cutting concepts to support three-dimensional learning that was held in 2018 at the University of Virginia, and brought together a lot of the leading researchers around the cross-cutting concepts. Okay, as we come near the end of the presentation, I hope that you've been inspired and empowered to meaningfully integrate the cross-cutting concepts in your classroom, but I also want to acknowledge that there are some challenges to doing that. And so we'll talk through a few of those challenges now. The first one is the challenge of focusing on meaningful learning. Kids often ask this question: why do we need to know this? What we want to do as we're engaging kids in three-dimensional instruction with the cross-cutting concepts, the core ideas, the practices, is we want to focus on knowledge in use. We want to focus on learning that happens just in time to help students answer a question, and not just in case information shows up on a test. So we want the learning to happen in a context in response to questions that students have in their mind. And that's kind of what those icons represent. The second part of that is we always want to think about who's doing the thinking. So we talked about the importance of scaffolding student thinking with the cross-cutting concepts, and we want to provide scaffolds, and students need those scaffolds, but we want to avoid scaffolding to the point where we just turn it into rote learning. We want to provide those scaffolds, but we always want to be pushing students to do the thinking for themselves. We don't want to take the thinking away from them. It's the same idea that doing a graphing worksheet is not the same as engaging in the practice of analyzing data. A second challenge and an opportunity comes from the structure of our standards. So if we look at the Georgia Standards of Excellence for Science, we might ask ourselves, well, where are the cross-cutting concepts? And we'll get two pretty different answers depending on which element we pick out. So we might find an element like SB1A from biology where there are explicit cross-cutting concepts, and in fact, there are three different ones. So we see structure and function, we see systems, and we also see stability and change connected to homeostasis. So in that case, I need to make a decision about what I'm going to focus on and how I'm going to meaningfully use those different cross-cutting concepts. At the other end of the spectrum, we might see an element like this one from sixth grade earth science, where there's not a clear cross-cutting concept. And again, this represents both a challenge and an opportunity. The opportunity is that it gives us choice as teachers. We can decide what cross-cutting concept is going to be most effective for my students in analyzing a particular phenomenon. It also provides the opportunity to give students some choice as they become more comfortable and more adept at applying the cross-cutting concepts. Then it would be terrific if we can put them in a situation of making the decision about which cross-cutting concept will be most productive in making sense of a particular phenomenon. The trick here, though, is that we need to remember that less is more. If we try to do all the cross-cutting concepts all at once, we won't do any of them well. So we need to focus in on one or two at a time. So in that biology standard, when I see those three different cross-cutting concepts there, I'm going to want to focus in on just one or two of those to best support my students. The other pattern that I noticed as I looked through the standards from this lens of trying to identify the cross-cutting concepts is that the standards where I had trouble identifying a cross-cutting concept tended to be standards that were pretty low level. If we think about DOK, they were more like DOK 1 type of standards, like this example from earth science, where essentially the standard is just saying kids need to know some information. And so by taking that, what's really just an informational standard, and adding in a meaningful cross-cutting concept connection, I can really increase the depth and rigor of that standard, and I can push my students to a much deeper level than just memorizing differences between comets, asteroids, and meteoroids. So I want you to take a minute and think about how you can make choices with your particular standards to best support your students. So look at the standards for your course and find an element that either emphasizes multiple cross-cutting concepts like that biology example, or that doesn't have a really clear cross-cutting concept connection. And think about which cross-cutting concept you would emphasize to support your students in making sense of phenomena related to that standard. Again, take a minute to think through that, answer that in the reflection guide, and then come back when you're ready to continue. The next challenge with the cross-cutting concepts comes in what's really their most fundamental role, which is connecting the scientific disciplines. And the biggest challenge here is just a practical one, that all of us at the secondary level in Georgia teach in a single discipline class. We teach earth science or physical or biology, chemistry, physics, etc. And so how do we connect different disciplines when we only teach that one discipline? Well, we're going to have to collaborate with our colleagues to do that. So if I'm a chemistry teacher, I'm going to have to reach out to my biology and physics and environmental science colleagues, and we're going to have to talk about, we're going to have to identify phenomena and plan to make intentional connections from one course to the next, from freshman year to sophomore, et cetera. Same thing at the middle school level. So work with your colleagues so that you can make some intentional connections from sixth grade to seventh grade to eighth grade. And the potential is there. It just takes sitting down for that conversation. And so we need to find time to do that. The second thing is that the disciplines are different. The cross-cutting concepts tend to emphasize the similarities, say, between biology and physics, but there are some real differences. And, this is just a version of a meme that I saw, but, to a physicist, all the structures on a bird just look like bird. And if I, as a biologist, look at physics phenomena and physics problems, I'm not an expert in that field. And so I'm not going to recognize the things that a physics expert would see and recognize. And so some researchers have really criticized the cross-cutting concepts for focusing too much on similarities and glossing over differences between the disciplines. But I think the much more important practical concern is students seeing the disciplines as separate silos. Students getting the idea that physical science and earth science and life science don't really have anything to do with each other. And so I think it's much more important that we use the cross-cutting concepts to help students see the connections, even though there are certainly some important differences. The final challenge, I think, is in some ways the most important one, and that's the idea that we have to build on student resources as we plan to integrate the cross-cutting concepts. And really, this goes for the whole three-dimensional model, and it really goes for all of teaching in general. We need to look at students as coming into the classroom and with all their varied backgrounds and experiences, and we need to see those things as resources to build on and not problems to overcome or to ignore. Students can achieve the goals we have for them only if we build on their intellectual and cultural and linguistic resources. That was another of the conclusions from that summit on the cross-cutting concepts. To do this, we can start by helping students become scientifically bilingual, meaning we help them connect their out-of-school language to what would be more formal, scientifically accepted language. We also build on their in-school and out-of-school experiences. So we connect back to this phenomena from previous classes. We connect to phenomena and experiences that they have outside of school, at home, and in the community. And in order to connect to those things, we need to know what those things are. So that's going to require us to talk to, again, our colleagues for those previous school experiences, and we're going to have to talk to the kids and build a better understanding of their experiences outside of school. And then once we understand those experiences outside of school, then we can really leverage those to select phenomena that students will find to be more compelling. I always remember the first time that I tried to do something that was sort of phenomena-based or project-based. I spent lots of time coming up with this great unit, and it was interesting to me. It was great science, and I presented it to the kids, and they could not have been any less interested because it didn't connect to anything that was important to them. If we can do these things, then we put students in the position of figuring out the answers to questions, of developing solutions to problems. And so by doing that, then we can really build their confidence, their agency or sense of self-efficacy, right? They can start to really see themselves as scientists and as engineers. And even if that doesn't lead to careers in science and engineering, it will lead to students who are confident in analyzing scientific information and making decisions based on the information outside of school. And finally, this all comes down to just valuing and providing space for students and the cultures that they bring into the classroom. And sometimes that means valuing culturally different ways of knowing, things that on the surface may not seem to match up to our Western science approaches, but that can also reflect some meaningful learning about the natural world. Okay, so I mentioned earlier that in your reflection guide, you'll find a list of resources. Here's a screenshot of what you'll see over in the reflection guide. It's listed as number 13. There's no prompt to respond to here, but I collected some great resources around the cross-cutting concepts and tried to organize those. So see some foundational documents, question prompts. We talked about that STEM teaching tools resource, but there are some other resources there. The graphic organizers we touched on. There are also a couple of NSTA blogs kind of describing how those were developed and also how they were implemented in some middle school classrooms. There's some just good basic resources like posters and symbols that you can use with your students, some professional learning resources, and then if you want to get nerdy, there's some links to some supporting research. Okay, and that brings us to the end of our session and to some final reflections. So really think about what you've learned today, how you can apply it, any questions you still have. I put that note there. We'll follow that 3 before me structure for answering those questions. So if you do have questions in your mind still, we're not in person where I can answer those. Check those resources I just shared with you. Talk to your colleagues and see what their thoughts are. Reach out to your online professional learning network. And then if you don't find a satisfactory answer, then please email me and I'll be happy to follow up and try to help you out. And then what's really important is think about your next steps. what can you do as school starts this year to be more effective in engaging your students and using the cross-cutting concepts to make sense of phenomena. I hope this has been helpful, and I look forward to hearing from some of y'all in the future. Y'all have a great year and take care.